Everyone, in today's video we are discussing about A to D and D to A conversion. A to D means we are converting analog signal to the digital conversion and digital inputs to the analog output. So here analog to digital conversion, how it is going to take, and digital to analog conversion, how we are taking, we are seeing with a small example. See, if we are giving an analog signal, what it will be in the waveform, and we will be having some wire impedance or noise distribution. There will be some disturbance occurred in the analog signal. Then we are using the filter to remove all unwanted noise and wire impedance. Then we are giving a sample hold which will connect the analog to the digital conversion, and that output what we got in digital, that we can convert again to the analog by using the smoothing of the filtering. So here the ADC gives digital output signal that can be easily processed, stored and transmitted by the digital system or the computer system. And even the DAC will converts, that is digital to analog conversion, will convert back digital to the analog. The typical A to D and D to A we can use in digital processing signal, digital audio mixing and data acquisition. So you can use this all in these three signals acquisition and mixing of the digitals. So first we'll discuss about digital to analog conversion. Here we have a basic diagram of DAC, that is we are using for n bit, that is from binary digit 1 to binary digit of n number, and we always know that the first binary digit is nothing but our MSB, that is most significant binary bit, and the last binary bit is nothing but our least significant bit, that is last binary bit. When we are giving input as our binary digit, our output is in the form of analog output. So here the DAC converts digital or binary data into its equivalent analog value. The bit B1 is called most significant bit and the Bn is called least significant bit. And if n is equals to 4, for example this I am taking for only 4 bit, then we'll have 4 bit DAC. Each digital input requires an electrical signal representing the logic 1 and logic 0. So here the output can be in the form of V0, K is nothing but your constant value, VFSS is your voltage reference, into binary digit of 1, 2 raised to power minus 1. Minus 1 is nothing but your binary number. Binary digit of 2, 2 raised to power minus 2, which is nothing but your binary digit number 2. So here V0 is equals to output voltage and VFS is nothing but your full scale output voltage, that is your voltage reference, and scaling factor is used, that is a constant value we are using. B1 to Bn is nothing but your n bit, and B1 as I said it will be always MSB and B2 will be always your LSB. So here parameters of DACs are nothing but resolutions. Resolution is one of the number of analog output value that is provided by the DAC. Therefore, n bit DAC is nothing but your resolution equals to 2 raised to power n. And resolution of the ratio of change in output voltage resulting from LSB at digital inputs. For n bit DAC, resolution is nothing but voltage output across the reference divided by 2 raised to power n minus 1. For example, I am taking 8 as my n bits and voltage reference, that is output is 10.4, so we'll get as 40.78 when we are giving the values to this resolution value, and hence we'll get to know voltage output is equals to resolution into B. B is any binary digit input we can take. Next parameter is accuracy. So comparison of actual output with expected output is called accuracy, and accuracy is equals to voltage output divided by 2 raised to power n minus 1 whole square. And another parameter is setting of the time, which will require the DAC output. Whenever we are going to have LSB as our final value, then it is a half, plus or minus half of the digital input. And stability, as the performance of a converter changes with parameters such as a parameter power supply variations. Our DAC is in two forms, that is binary weighted register DAC, R2R ladder DAC. So binary weighted register DAC, what we are going, we are connecting our all inputs to the inverting terminal and giving our voltage follower also to the inverting terminal, which is having the resistor F and current IF. So our positive, that is non-inverting terminal, is given to the ground. As we are giving our input, we are not directly giving from the inverting terminal, we are also giving our voltage reference as our input, which is connected all the registers and binary digits parallelly, and all we have the switches. So here we have n bit of switches, we can have n number of switch which is independent of each binary digits. So the DAC is one of the simplest circuit of n bit. Op-amp is used to sum n number of binary bit, which is derived from the voltage reference VR and current scaling the register. If binary input is very high, then we are saying it gives the output 1, and if it is less, we are telling it is giving the output 0. So here when we say binary number is 1, when it is 1, it is when the condition is in on state and our current flowing is voltage reference by total resistor. So when I am giving the current, what I am getting, voltage reference divided by resistor. If this binary digit is 0, that means my condition is off, that is this switch is off, that time current is not flowing, so 0, it is ideal. So the total amount of current through RF, it is flowing IF. So here IF is nothing but summation of all the current of the parallel resistors. So here I1 plus I2 plus I3 plus IN. So what we are getting, voltage reference divided by 2 raised to power 2, 2 raised to power 1. Here this is nothing but your n. N is nothing but your binary digit value. So for binary 1 we have 2 raised to power 1. For binary 2 we have 2 raised to power 2. So n number we can have n number of bit and n number of binary digits. So we are getting IF is equals to voltage reference divided by R. If we are taking this in multiplication, what will happen? It will happen minus 1. Binary digit of 2 into minus 1, binary digit of 2 into minus 2, so on till n. And we know our voltage output across RF is V0 equals to, as it is inverting terminal, we are taking minus IF into RF. So if we are substituting our IF value in this formula, what will get? V0 equals to minus VR, that is voltage reference divided by R into RF, binary digit of 1 into 2 raised to power minus 1 till binary digit of n. Here we say that RF is this R and register R across the each binary digit is equals to register of the voltage reference, then we'll get final output as this.